Hello, I am Ahmet Eren Kartal. I am a second year student at Bilkent University Electrical and Electronics Engineering Department. In this video, I will be presenting our Physics 212 project, which is called Random Number Generation via Stochastic Radioactive Decay. The goal of this project is to build a system that generates truly random numbers. To achieve this, we use the unpredictable timing of radioactive decay events as source of our randomness. Random number generators are categorized as two types. The first type is called a pseudo-random number generator. A pseudo-random number generator uses a deterministic algorithm to produce a sequence of numbers that appears random. However, if the starting value of the algorithm is ever known, the entire output becomes predictable. The second type is called a true random number generator. A true random number generator extracts randomness from a physical process rather than a formula. A special subclass of true number generators are quantum random number generators, which use process governed by quantum mechanics. Radioactive decay is one such process. According to quantum mechanics, the exact moment a nucleus decays cannot be predicted. On a statistical level, the number of decay events in a time interval follows the Poisson distribution. The Poisson distribution describes the probability of observing exactly k events in a time interval given an average decay rate lambda. To use the randomness in radioactive decay to produce random numbers, we built a hardware system using the following materials: a Geiger-Müller counter, an Arduino Uno microcontroller, an computer, an oscilloscope, and three radioactive sources: strontium-90, cobalt-60, and cesium-137. The Geiger-Müller counter detects ionizing radiation events. Each time a decay event occurs, it produces a short digital pulse. The Arduino reads this pulse and measures the time between two consecutive ones. We call these times T1 and T2. The bit generation rule is simple. If T1 is greater than T2, we output a binary 1. If T1 is less than T2, we output a binary 0. If they are equal, we discard the result. In addition to using a radioactive material to produce a bit stream, cosmic background radiation is also used. Furthermore, we measured the number of ticks per second for each radioactive material to verify the Poisson distribution. To evaluate the quality of the generated bit sequences, we use the NIST statistical test suite. This is a standard tool published by the National Institute of Standards and Technology for testing random number generators intended for cryptographic use. The test suite contains 16 different tests. Each test returns a p-value. If the p-value is greater than or equal to 0.01, the sequence passes the test and is considered random. For the strontium-90 source, all four tests passed with a 100% success rate. The monobit test gave p-value of 0.92, confirming that zeros and ones are distributed with nearly equal frequency. The runs test gave a p-value of 0.92 as well, confirming that the transitions between bits occur at the rate expected from a truly random process. For cosmic background radiation, all four tests also passed. However, the monobit and runs p-values were lower, around 0.21 and 0.32 respectively. This is likely due to the much lower event rate of cosmic radiation, which resulted in a shorter and noisier bit stream. In the second part of our experiment, we investigated whether radioactive decay truly obeys the Poisson distribution. To verify this, we recorded 180 measurements of ticks per second for each of the three radioactive sources. We then plotted the observed frequency distributions and overlaid the theoretical Poisson curve using MATLAB. To quantify how well our data matches the theory, we performed a chi-square goodness of fit test. This test calculates the difference between the observed counts and the expected Poisson counts. If the results falls below a critical threshold, we accept that the data follows the Poisson distribution. All three sources passed the test. This means we successfully proved that radioactive decay obeys the Poisson distribution. Overall, in this project, we successfully built a system that generates three random numbers from radioactive decay, and we verified the randomness of that output using the NIST statistical test. Also, we proved that radioactive decay obeys the Poisson distribution. Thanks for watching.